Okay, let's look at the sharing bridge. Okay, so sharing bridge is the basic circuit to measure tan delta of an insulation material. Okay, so this is the sharing bridge circuit as per the IEC standard, IEC 60034-27-3. So this standard is for rotating machine, measurement of tan delta for rotating machine, motor, generator. Okay, so we use the standard. So in the standard provides the basic circuit for sharing bridge. Alright, so as you can see here, we have high voltage AC supply. Alright, so this is the voltage supplies, the voltage that needs to be supplying voltages across the insulation material, the test object. So the bridge has 4 arms. Okay, arm number 1, arm number 2, arm number 3, and arm number 4, and it has null indicator at the middle. Okay, the function of null indicator is to indicate that the bridge is in balance condition or not. Okay, because we have to make the bridge balance to determine the value of the insulation material, to determine the value of tan delta of the insulation material. Right. So usually the test object is in arm number 2. Okay. Alright, so Phasor diagram and circuit model for a non-ideal capacitor. Alright, so instead of in previous video, I have showed you the R and C and R in parallel, but this case it is C and R in series. Okay, it can also be represented in series. Alright, so in series, the total current is in horizontal. The voltage is now is behind the current. Alright, now the tan delta is this. Okay, this is the tan delta. Okay, so if the insulation is represented in RC series, so we have to analyze the Phasor diagram. Okay, using this setup, this arrangement. Okay, so current is now fixed, voltage is now changing. Alright, from VC to here if there is a loss in the insulation. Alright, so this is VC plus VR is the total voltage. VC VR, this is the total voltage. So if there is dielectric loss in the insulation, then the resistance will also increase. So if the resistance increase, then the voltage will also increase. So the voltage VR will increase in magnitude. In that case, the tan delta or the delta value, the angle of delta will also increase. Alright, so you can see here tan delta is basically VR over VC. Okay, this if the insulation is represented in series, RC in series. Okay, RC in series, tan delta is VR over VC. RC in parallel, tan delta is IR over IC. Alright, so let's look at the sharing bridge circuit. Okay, from this circuit, the sample of the dielectric is represented by the series model of CX and RX. Okay, so this is the sample or the insulation that is going to be tested, insulation material that is going to be tested, which is represented by R and C in series. Okay, so this is in arm 2. Okay, arm 1, arm 2, arm 3, arm 4, and this is the null detector that we need to balance the detector. Need to balance the bridge by looking at the detector. Okay, the first arm number 1 is a gas field standard capacitor, CS, gas field standard capacitor. That is a fixed value. Okay, the capacitor has fixed value. The third arm 3, right? This one has variable resistor R3. Okay, has variable resistor, that is in arm 3. And then the fourth arm, variable capacitor C4 in parallel with fixed resistor R4. Okay, so we have two variables here, two parameter that we can change, that we can vary, which is R3, the resistor in arm 3, and then the C4 capacitor in arm 4. Okay, so in practice R4 value is constant and C4 is variable, so we change C4, we change R3. So this C4 bridge value is calibrated or tuned to obtain a constant value of frequency, may be observed by a detector. Alright, we observe detector, we tune this and observe at the detector, and then from the circuit the dissipation factor tan delta can be determined based on the observed frequency C4 and R4 values. Okay, so we tune or calibrate the value of C4 and check the value of R4 as well. From this we can when the null detector is at the middle, is at balance condition, then we can determine the value of Rx and Cx. Okay, so tan delta equals to omega Cx Rx, which is also the same as tan delta equals to omega C4 R4. Okay, this is the explanation why tan delta is equals to WCX Rx, which is also equals to WC4 R4. So you can see here, if we can this condition only true if the detector is in balance condition. Okay, if the bridge is in balance, then omega Cx Rx is equals to omega C4 R4. Means that we know now the detector is in balance, the bridge is in balance. From the value of C4 we know that Cx is also C4. We know that Rx, the insulation dielectric loss, is also the same as the resistance of R4. Okay, because balance, this value is equal to this value now. That's the idea. Okay, so at balance the bridge is so Zx equals Z2 equals Z1 times Z3 Z4. So basically this is the balance condition of the circuit. You can hang on, let me see, this is Z1. Okay, sorry, not Z4, is Y4. Okay, so Y4 is basically same as 1 over Z4. Okay, so Y4 is basically equals to 1 over Z4, right? Z is the impedance, Y is the admittance. Okay, admittance is the inverse of impedance. Okay, so Y4 is basically 1 over Z4. 1 over Z4, so if 1 over Z4, we move Z4 here, so it means that Z2 times Z4 equals Z1 times Z3. Okay, Z2 times Z4 equals Z1 times Z3. Okay, so in this case Z4 when we move to here, it is 1 over Z4. So 1 over Z4 is equals to Y4. Okay, so hopefully you can understand that. Alright, so basically Z1 is 1 over J omega CS. Same thing, Z2 Rx1 plus 1 over J omega Cx. Z3 we have R3 1 over Z4, or inverse of that is Y4, is equals 1 over R4 plus J omega C4. Okay, this is basically inverse of 1 over inverse of Z4, right? So in this mathematical explanation, it uses Y4 because easy to solve the solution. Okay. Alright, so basically we solve this. Rx minus J omega Cx equals to J omega R3 and so on. Okay, you can just fill this value here. Okay, replace the value Z1, Z3, Y4 here, and then we separate the real and imaginary terms. You can get that R4 is the real component. Okay, real components equals to C4 over Cs times R3, and then from this term, the imaginary terms, the imaginary components, which is Cx here. Okay, J over omega Cx, that is the imaginary terms. Cx is equals to R4 over R3 times Cs. Okay, so Rx is this value, Cs is this value, and then going back here, that we have proof that for RC in series, the tan delta is equals to omega Cx Rx. So from here, omega Cx Rx, we replace Cx with this, we replace Rx with this, and then from that we can prove that it is also equals to omega C4 R4. Okay, so this you can try your own, right? So this is for R and C in series. So I have explained this in previous video. Alright, so R and C series in just before, and this is R and C in parallel in previous video. Okay, so this is just to give you an idea the actual measurement of tan delta at site in the industry, what the industry is practicing. Okay, so here this is actually a large motor. Okay, so you can see here it is a 3-phase motor, 11 kV. Okay, 11 kV high voltage 3-phase motor. So you can see here the cable, 11 kV cable, is connected to the terminal of the motor. Here we have red, yellow, blue, or usually for motor we use the terminal UVW. Okay, so UVW, if you can see here, the cable is removed from the motor, and we have red and black cable coming from here. So this is to inject that high voltage supply. This is to inject high voltage AC supply to the test object. See here, this is plus, this is minus. Okay, supply high voltage to the test object, and this is the bridge. The other part of the bridge, arm number 1, arm number 3, and arm number 4 is actually inside this equipment. Okay, so the sharing bridge is basically inside here, and we can obtain the equipment will automatically give the value of tan delta. Okay, will give the value of tan delta, and this is for high voltage rotating machine. and this is for same thing using the same equipment. We perform measurement on power transformer. This is 33/11 kV power transformer. Okay, so we perform tests on the insulation of the power transformer. Okay, so in this case we perform insulation. We perform tan delta test on the insulation of the stator winding of the motor. In this case we perform tests on the insulation of the power transformer between HV, insulation between HV and LV, insulation between HV and ground, insulation between LV and ground. So any insulation that we have in the equipment, we perform tan delta test to evaluate the condition, to assess the condition or the status of the insulation. If the tan delta is good, is very low, then the insulation is good. Alright, so an example, after 1 year, after several months, we perform the tan delta measurement again, and then if the tan delta value somehow increase, that indicates the insulation is aging, is deteriorating, indicating that the insulation has problem, because after certain time, certain period, if the tan delta value increase, then must be because of some losses occurred in the insulation. So as an example of a calculation, we have one example of calculation. Should I put this? Okay, a shearing bridge used to measure the capacitors and dissipation factor of a high voltage bushing at 50 Hz. Okay, so the measurement gave the following results at balance. Okay, based on shearing bridge, when the bridge is in balance condition, arm number 1, the value of the capacitor. So we have arm number 1, CS, that is the standard condenser of the capacitor. The value is 100 PF, picofarad. Arm number 2, let me see here. Probably there is a mistake here. I believe this should be arm number 3. Okay, so this is arm number 3. My mistake. This is arm number 3. So arm number 3 is a resistance with 720 ohm. The variable resistance is at 720 ohm, 720 ohm. And then arm number 4 here, we have capacitance C4. Capacitance C4 at 1200 picofarad in parallel with the resistance of 3315 ohms. Alright, so we have this value for arm number 1, arm number 3, arm number 4. Okay, you determine the capacitance and dissipation factor of the bushing. So this is arm number 2 is basically insulation of the bushing. Okay, so if you do not know what is bushing, just Google image bushing. Bushing is basically a part of transformer. Okay, cannot be seen from here. It's basically a part of transformer. So can we determine the capacitance and dissipation factor of the bushing? Yes, if we have all this value, arm number 1, 3 and 4, we have the equation. So just replace the value, simply replace the value. Alright, so we have the value. What is CS C4? Alright, just replace the value here, then you can get the value of the tan delta. Alright, tan delta and the value of the capacitor. Okay, so tan delta is equals 0.00125. Okay, however, in practice, okay, this is in practice. In practice, usually we multiply the value in we give the value in percentage. So meaning that this value needs to be times multiplied with 100, and we have percentage. So This value usually we present as 0.125%. 0.125%. Okay, because we multiply with 100, so the value is easy to represent in percentage, 0.125%. So that is good, very low. So if the value increase 0.5%, then we have to take note, must be something wrong with the bushing. Then after that, if the value also increase, and then we have to replace the bushing. Okay, so that's the idea of tan delta test.